Hello everyone and welcome back to the next lecture of control systems. In this presentation we are going to discuss the problem number 2 based on transfer function. So let's get started. Find the transfer function of the following RC circuit. The RC circuit is given to us. The input VIT is applied into the circuit and the output VOUT is measured across the resistor. If you remember, in the previous problem, the output voltage was measured across the capacitor, and now we have changed the arrangement and the output voltage now is measured across the resistor. And we need to find out the transfer function. And we know the transfer function is the Laplace transform of output to the Laplace transform of input, assuming all the initial conditions equal to 0. So the step number 1 is to find out the Laplace equivalent circuit. So moving on to the solution, the Laplace transform of VIT is VIS, the Laplace transform of VOUT is VOUTs, the Laplace transform of resistor is R, and the Laplace transform of capacitor is 1 over SC. In this problem, we will discuss that how the Laplace transform of a capacitor is 1 over SC. So now we have the capacitor C and we need to analyze this capacitor in the Laplace domain. So by finding the Laplace transform of a capacitor, we actually find the impedance offered by this capacitor. So if IT is the current through this capacitor and due to which VT is the voltage developed across it, if we apply Ohm's law, we can write IT is equal to C multiplied dVT over dt. This is the Ohm's law for a capacitor, where IT is the current through this capacitor, C is the capacitance of this capacitor, and VT is the voltage developed across this capacitor. Now if we apply Laplace transform to this equation, we will have IS is the Laplace transform of IT is equal to C. C is a constant because it is the capacitance of a capacitor. So C will be taken out and we will apply Laplace transform to derivative of Vt, and its Laplace transform is given as SVS, where Vs is the Laplace transform of Vt. Now if we take the ratio of Vs over Is, we will get the impedance offered by this capacitor into the circuit, and it is given as Vs over Is is equal to 1 over SC, and in this way the Laplace transform of a capacitor is given as 1 over SC. So now we know that how the Laplace transform of a capacitor is given as 1 over SC. We will continue with our solution. The Laplace equivalent of this circuit is given by this circuit, and now we have the Laplace equivalent of capacitor is equal to 1 over SC, the Laplace equivalent of resistor is equal to R, and the Laplace equivalent of VIT is VIS, and the Laplace equivalent of VOUT is VOUTs. And now we need to find out the transfer function, which is the ratio of Laplace transform of output to the Laplace transform of input. So for that sake, we need to find out the output voltage which is measured across this resistor, and then after that we will take the ratio VOUTs over VIS to find out the transfer function. Now in this circuit, if we observe this node, then if I ask you what are the number of branches connected to this node, then what will be your answer? 2 or 3? No, it is actually 2 because it is an open circuited branch, so no current will flow into this branch. So we have only 2 branches. In one branch capacitor is connected and in the other branch resistor is connected. So if a current is flowing in this capacitor, the same current will flow into this resistor and no current will flow in this open circuited branch. So we can say that the current in this capacitor and this resistor is same, and that's why the capacitor and resistor are in series. And in series, the voltage gets divided. So we can find out the output voltage which is measured across this resistor by using the voltage divider rule, and it is given as V0s is equal to VIS, which is the total input voltage, multiplied with the impedance of this resistor, which is equal to R, divided by the total impedance of the circuit, which is R plus 1 over SC. Now we want the ratio of the output to the input to find out the transfer function. So if we transpose Vi of s to the left hand side, we will have the ratio V out s over Vis, and this is our transfer function, and it is given as R over R plus 1 over Sc. Now if we take the LCM, then we will have the transfer function, which is the ratio of output voltage to the input voltage, is equal to Rs multiplied with C divided by Rsc plus 1, and this is the transfer function for this RC circuit. So now we are done calculating the transfer function of this circuit, and now we will compare the RC circuits that we have discussed in this lecture and in the previous lecture. Now moving on to the comparison between these two RC circuits that we have discussed till now, the major difference is the measuring of output. The output in this RC circuit is measured across the resistor, and the output in this circuit is measured across the capacitor. The transfer function for this RC circuit is given as H of s is equal to 1 over 1 plus Rsc, and the transfer function for this circuit is H of s is equal to Rsc over Rsc plus 1. The differentiating factor between the two circuits is the capacitor, because the impedance of capacitor is 1 over Sc, and S is the frequency dependent term. If we change the frequency, the behavior of the capacitor will change, and hence the behavior of circuit will also change. Let's understand this in a better manner. The impedance of capacitor is 1 over Sc, and S is equal to sigma plus j omega. Omega is the frequency by which we are providing the input, and if we change the frequency, the behavior of capacitor will also change. If we observe the impedance of capacitor, Xc is equal to 1 over Sc, and S is a frequency dependent term, so we can say that the impedance of capacitor is inversely proportional to the frequency. So when the frequency is low, the impedance will be high, and when the frequency is high, the impedance will be low. And that's why we say that for low frequencies the capacitor acts as open circuit, and for high frequency the capacitor acts as short circuit. Now if we give low frequency signal to this particular circuit, then this capacitor will act as an open circuit, and if there is an open circuit in place of this capacitor, then we will get some output voltage. But if we increase the signal frequency and if we pass high frequency signal to this particular circuit, then this capacitor will act as a short circuit, and if this branch is shorted, then the output voltage will become 0. So we can say that for low frequency signal the output is non-zero, and for high frequency signal the output is equal to 0. In this way this circuit acts as a low pass filter, and that's why we call this filter as the RC low pass filter. The filtering characteristics of RC low pass filter is shown by this graph. On the y-axis we have the output, and on the x-axis we have the frequency of the input signal. We can observe that when the signal frequency is low, the output is non-zero, and when the signal frequency is high, the output is 0. And the reason behind this is the short circuit behavior of capacitor in case of high frequency signal. So we can say that whenever we measure the output voltage across the capacitor, then the RC circuit will act as a low pass filter. Now moving on to this circuit, if we observe, the capacitor is connected to this branch and the output is measured across the resistor. Now if we pass low frequency signal to this circuit, then the capacitor will become open circuited and the input will not reach to the output. And that's why the output signal will be 0 for low frequency input. But in case of high frequency signal, the capacitor will act as short circuit and the output is obtained. And that's why we can say that in this circuit, for low frequency signal, the output is equal to 0, and for high frequency signal, the output is non-zero. And that's why we call this filter as RC high pass filter. The filtering characteristics of RC high pass filter are shown with this graph. We have the output on the y-axis and the frequency on the x-axis. For low frequency signal, the capacitor acts as open circuit and that's why the output is equal to 0. But for high frequency signal, the capacitor acts as short circuit and that's why the output is non-zero. So we can say that this filter blocks the low frequency signal and it only allows the high frequency signal. And the starting frequency from which it allows the high frequency signal is the critical frequency. Similarly, in case of low pass filter, the highest frequency up to which the filter allows the low frequency signals is called as the critical frequency. So we can observe that in case of low pass filter, the critical frequency is the highest frequency, and in case of high pass filter, the critical frequency is the lowest frequency. And it is the lowest frequency because after this frequency, the output is non-zero. But in case of low pass filter, after critical frequency, the output is equal to 0. But before critical frequency, the output is non-zero. So now we are done with the comparison of these two circuits, and now we can easily differentiate the RC low pass filter and the RC high pass filter. Thank you for watching this lecture. I'll end this lecture here. See you in the next one.